Alright, welcome to part 2 of gravity. This is primarily focused on falling objects, with a little bit still on center of gravity. So, let's talk about falling objects. At this point, you've probably seen in class or in your life dropping different objects. You've probably seen that no matter what the object, they all fall at the same rate. So, that means that if you drop a book, or a pencil, or a marble, or a paper clip, or an elephant, or a chicken, or whatever, it all falls at the same rate. Everything accelerates at 9.8 meters per second squared. So you drop your pencil, your book, they all accelerate at the same rate. But you're probably already thinking, well, what about a piece of paper, or a feather, or things like that? And you're right. There are some things that don't. We're going to talk about that. But first, let's just talk about how this makes sense with something that does fall at the same rate. Pencil, book, so on and so forth. So, let's just say your pencil is 1 kilogram, your book is 2 kilograms. Remember, force equals mass times acceleration. So therefore, if the mass is 1 kilogram, the acceleration is this, the force would be that. So your more mass ends up being more force, so the acceleration stays exactly the same. So if mass goes up, that means that force goes up. But acceleration stays the same. So think of it, if you're dropping a pencil, you're dropping an elephant, the elephant's going to hit the ground a lot more force, than the pencil will. But they still accelerate at the same rate. So when you increase the mass of an object, it's just the force that goes up. It's not the acceleration. However, you've probably seen that that's not always the case. So let's talk about some cases where you don't always fall at exactly the same rate. So this skater here on Earth falls at this rate. If we moved him to the moon and dropped him there, he would not fall at the same rate. So the first thing that's going to affect different objects falling has to do with the amount of gravity, or the force in general. So if we go to Jupiter here, where there's a lot more gravity, he falls quicker. So if you have more gravity, you are going to accelerate more quickly as opposed to something that has less gravity. And the same idea, it's just because gravity is more force. So more force, in that case, would be more acceleration because your mass is staying the same. However, there are instances in which not everything does fall at the same rates. So you have, like I said, your piece of paper and, let's say, a crumpled piece of paper. So let's take a look at this. So let's see if we can figure out why. So you drop a piece of paper flat, it floats down to the ground, but as soon as you crumple it up, now it goes down at a quicker rate. How is that possible? So what's really important to realize here is that, once again, everything wants to fall at the same rate, but it doesn't here on Earth because sometimes you have forces going against gravity, which we have is air or fluid friction. So that's the main factor here. So you really need to go back to balanced forces and unbalanced forces to kind of remember what's going on here. So when you have your paper kind of flat like this, you have the downward force of gravity on each of the little sections of paper, because each little section has a very, very small mass. So each little section is only being pulled down with a little bit of force. And the fluid friction is pretty much the same as the force pulling down. So when you have the fluid friction like this, which is pretty much the same as the force pulling down, it ends up not making the paper accelerate. It goes down kind of slowly, or even close to a constant speed. So that's what's happening here, is that the force pushing up from the air is pretty much the same as the force pushing down on the different sides of paper. But when you crumple it up now, you put all that mass that was in the paper all condensed into one spot, essentially making it more dense. So now in this little section of paper, you have more mass in this little section, and more mass in this section, and more mass in this section. So because you have more mass now, it means you have more force. So the force now is greater than the force of the fluid friction, and it can easily go through the air. So that's the main difference, is you're basically combining all these forces and condensing them into one place, if you can think of it like that. But the fluid friction is staying exactly the same. We're not doing anything to the air below it. We're just taking all these little forces and pushing them all together, so we have more mass and more force in one area. So that's why the crumpled paper falls faster than the fluid paper. But an interesting example here is, you hopefully saw this example where you take a paper and you place it on top of a textbook and you drop the textbook, and the paper doesn't float down, it goes straight to the ground. So what's going on here is that you have your paper with the downward force of, again, not a whole lot, the fluid friction with the same pretty much as the paper. The main difference here is you have a book or something that's heavy, so the heavy object has a lot more force. So now if you kind of take away the paper, what's going on here, this book can go through this fluid friction without any difficulty at all. So it kind of flies right through there without slowing down. And because this paper here is blocked by this book, it gets no fluid friction to slow the paper down. Remember, the only reason the paper slows down in this previous one is because there's air underneath it to slow it down, and therefore fluid friction. But if the book is there, it basically blocks all the fluid friction, so none of it hit the paper. And since the book is higher mass, it can go right through the fluid friction. There's a really great video or two that I have on the playlist that is the feather and the hammer on the moon, and the feather and the bowling ball in the vacuum here on Earth. And it really shows that when you go to the moon or a vacuum that basically gets rid of all this different stuff here, all the air, then a piece of paper or a feather will go down at the same rate as everything else. So it's really just air that messes everything up. Alright, now, I'm going to do my best to explain this, but I highly recommend, once again, you check out those, at least that one video about skydiving, and there's another one that's a little bit more advanced, but on the topic of terminal velocity. It's complicated, but like I said, I will do my best. So what terminal velocity is, in the easiest description, it's that everything accelerates at 9.8 meters per second squared, but at some point, every object here on Earth has a maximum speed. So if you're a skydiver, as you skydive and you drop out of a plane, you start getting faster and faster and faster and faster and faster. And I think it's around 180, maybe 200 miles an hour, that you kind of max out your speed. You don't go any faster. And there is a reason for that. And it's called terminal velocity. So it's easier to see with the example we did in class with a cup, or we haven't done it in class. If you drop a cup, it's a plastic cup, you'll see that it starts to accelerate, and then it seems to slow down. And it doesn't slow down, it just stops accelerating. So let's talk about why that's happening. So let's say we drop our cup here, alright, and we have the ground down here, just so we have kind of a reference point. Alright, so if we drop our cup, what happens is when it first starts dropping, the force of gravity is pulling down on the cup. This is going to represent the force of gravity. This does not change. The cup's not getting any bigger, the Earth isn't getting any more massive, so the force of gravity stays the same the whole time it's dropping, so it stays like this. But what changes is the amount of air hitting the cup. So when it first drops, there's not a whole lot of air hitting the cup. But then as the cup gets a little bit faster now, because it's going faster, it means that more air is hitting it every second. And then it gets a little faster, and then more air is hitting it every second. So the fluid friction keeps going up and up and up, and eventually it gets to this balanced force. So again, you go back to balanced forces. So when it gets a balanced force now, what that means is that the cup will stop accelerating and it starts going at a constant speed, because all the force of the air is exactly the same as the force of gravity, and for the rest of its trip down to the ground, it will travel at a constant speed. So that's why you hear rumors and stories about throwing a penny off the Empire State Building and it can go through a person's skull. I don't believe it would. It would hurt them for sure, but a penny hits a maximum speed pretty quickly and it stops getting faster and faster and faster. So actually, when you drop a piece of paper, what's happening there is it starts to accelerate, and almost immediately the forces below the paper, like a flat piece of paper, are the same as on top, so it travels down at a constant speed. So like I said, check out that skydiving video so you can get the idea of terminal velocity, but basically when the force of air becomes the exact force of gravity, then it maxes out its speed and it starts then traveling at a constant speed. So now we're going to talk about one of my favorite questions that we went over in class, and that is, if you shoot a bullet and you drop a bullet, which one will hit the ground first? And this is one of my favorite questions because logically, pretty much all people, including myself when I first learned about this, I said the bullet you dropped would have to hit first as opposed to the bullet you shoot out. So what we're going to do here is prove that that's not the case, and they actually hit at exactly the same time. So you want to just keep an eye on this time over here. So let's say we shoot the bullet out here. Okay, it hit the ground in 1.9 seconds. Now let's make it half the speed when we shoot it out, so we shoot less force. It doesn't go nearly as far, but it takes 1.9 seconds. And then let's just say we make it 40. I don't know if this is even going to stay on the screen or not. Fires off the screen, wherever it landed, far away, but it still hit in 1.9 seconds. And then this you're going to have to almost take our word for it here. Let's just make it 200, which is kind of like, I guess, a speeding bolt. It just shoots straight out. But somewhere down this line here, at 1.9 seconds, it has hit the ground. It's going slightly down here. And then, if you simply drop a bullet straight down, it takes 1.9 seconds. So in this case, it happens to be 1.9 seconds every single time. And that would change if we adjusted the height of the cannon. It would be different, than 1.9 seconds. But you see the idea here. X represents how far it is after 1 second. So no matter how hard I shot it, after 1 second, it's the same. So again, I have a video that I put in the playlist that you should definitely check out. And the explanation to this is simple, yet, I guess, tricky at the same time. So what it is basically, gravity is a vertical force. And forces, in the world of forces, if you're not having some sort of vertical force, it's not going to affect gravity. So if you shoot something straight out, like this, it has no effect on gravity because gravity is a vertical force and shooting something out is a horizontal force. If you were to shoot something in the air like this, then yes, it would take longer to hit the ground, or if you shot something down, then it would go quicker to the ground, which is common sense, but it's just going to show you. So if you angle it down at the ground, now it's 1.7 seconds. And if you angle it up in the air, now we're at 2.7. Oh, I scored. Nice. But the point here is that as soon as you adjust this so it does become a vertical, this would take longer, this takes shorter, but as long as you're right here, flush with the ground or parallel with the ground, then it would have no effect on how fast it falls. It falls exactly the same rate. Alright, so now we get into our final topic of gravity, and that is center of gravity, or as I kind of like to think of it, when things fall down. So, like I keep saying, I have 2 videos on my playlist that are really good, but I'll give you my little short explanation. And basically, here's what it is. Every object has a center of gravity. It's the spot that you can basically balance something on. So if you were to hold a ruler on your finger, you can go ahead and try that right now if you'd like. You hold a ruler on your finger, the spot where you hold it, and it balances, that's called the center of gravity. And every object has it, and it's basically the spot where it balances. And in people, it's usually right around your belly button. So as long as your center of gravity doesn't go beyond your base, so your base is essentially the area between your feet, then you won't fall down. But if you lean over, and as soon as your center of gravity goes past your 1 foot here, it will make you fall over. Like I said, the video I have does a better job explaining it with pictures and animations and stuff, but this is getting right to the point. If your center of gravity goes past your base or your feet, then you will fall over. But what's tricky is you hopefully saw this example about forks on a beaker or a cup. This is a fun trick you can do at home. And in this case, your center of gravity is actually kind of not anywhere on the forks, it's between the forks. But the point is, the spot right here where it balances on the beaker is the center of gravity, which means that there's equal mass on either side. So it means that this is 35 grams on this side of the dot, and then if you add up this section and this section, it would be 35 grams as well. So I had this donut up here because, as an example of where a donut center of gravity would be kind of right in the middle. So it doesn't necessarily have to be on the object itself. This is tricky, but the main idea here is that if you actually look at this, there's as much mass behind the beaker on this side of the toothpick as there is on this side. It's kind of an optical illusion. So this kind of sums up objects falling and center of gravity. Hopefully you learned something today, and as always, to my students, please, if there's anything you need help on, make sure you ask for help and let me help you out, because gravity is tricky and I want to make sure that you understand this. So take advantage of the resources I gave you, all the videos and interactive animations, because I really think that they're going to help you as well. Alright, thanks.